Hi guys, this is Tom from CodeJoint here, and the topic for today's tutorial is threading in Unity 3D. It's a really exciting and important area in modern programming, so I think it's important that you understand the applications of threading to Unity. I'm going to be talking about what threading is, when you can use it in Unity, what you can't do with threads in Unity, and then I'll give a couple of examples, and in particular using queues to perform background tasks, and I think that's actually quite an important and useful topic in games programming. So if you're not aware of what threading is, basically it's utilizing the multi-core structure of modern CPUs to perform 2 or more tasks concurrently. So if you go back, say, 13 or 14 years, all processors just contained one core. And that meant that there was only one processor that could perform tasks at one time. Now, modern CPUs can have several cores, so that means that each of those cores can basically act like one processor and do its own jobs independently from each other. And if you just write standard C# or any standard code, you're only making use of one core, so you actually have to write special code to make use of multiple cores. So various applications include running long calculations in the background whilst keeping a user interface responsive. So this means that if you're doing Windows Forms programming, for example, or WPF, you want your user interface to be able to respond to the user whilst you're doing heavy tasks in the background. So you want to be able to move windows, resize them, maybe save, or various other tasks that you might run in your program. Also, you might want to use, for a given task, you might want to try different algorithms to see what is the most suitable for a given job that you're trying to complete. And whichever one completes first, then that's the one that the answer that you use. So you might want to use multiple cores to run each of the different algorithms separately, and then see whoever gets there first, and then just abort the rest of the algorithms before they complete. Another thing that you can do is you might have one big task, but you might be able to split it up into smaller tasks, and you might have your cores threaded so that you can each core will do one particular subtask, and then at the end, when they're all completed, you collate all the information together at the end. So anyway, now let's talk about threading in Unity, and why should you use threading in Unity? The main thing is that if you use threading correctly, you can significantly improve the frame rate of your game. So Unity is single thread at the moment. All the I'll talk about this in a moment, but all the Unity functions aren't thread safe, so that means you can only use them on one core at a time. But if you have various tasks in your game that you think that you can delegate to other processors, then you can really take the load off your main thread, i.e. your update thread, and improve the performance of your game. So things that you can thread, for example, is your creation and updating meshes. Maybe you have some plugins that you're using, external plugins for Unity, and you might want to thread them. The only drawback of threading is that it can be a little bit dangerous if you don't really know what you're doing. And although this might sound a bit daunting, it doesn't actually take that much work to figure out how to use threading. And I hope this video anyway will help you in that journey towards becoming a multi-core programmer. The problem lies in that if you're sharing information between threads, you can sometimes get unpredictable behavior when threads are trying to access the same information, one piece of information at the same time. But there are ways that you can ensure that this doesn't happen using various keywords. So the word for code which isn't safe and is unpredictable is thread unsafe, and code that makes sure that only one thread can access variables at one time is called thread safe. Don't be too scared by this, as I actually found out I was pretty scared about this, if I'm honest, at first when I started using threading, but I found out it was actually pretty easy after a while. So just to explain what I mean by thread safe and thread unsafe, I've got an example of some pretty unsafe code. Now, this code here, it's a simple class that I've put on a game object, and in the start, what we do is this line here starts a new thread which runs this multiply method. And all this multiply method does is basically prints to the console what these two floats, x times y, what their product is. And then we update y to be the product of that. Now, after this new thread is initialized, we increment y, and then we run multiply on the main thread. So multiply is being run on a new thread and the main thread concurrently. And the result you might expect, if you have a look at the order of this the start method, is that you would expect the multiply on the new thread to print out 0, because x times y would start as 1 times 0, which is 0. So if you're unfamiliar with threading, you might expect the first debug result to be x times y is 0. But in fact, on my computer, it actually turns out as the first print statement you get is x times y is 1. And the reason why that is because before this debug.log command method can complete, or it actually gets to this part where it's printing it out, y is changed on the main thread. So this is what I said a moment ago about code being about variables being shared between threads. Before it's had a chance to actually print it out, y is incremented on the main thread. Now you might not expect that, and this can lead to, this is just a very simple example, but you can get more complicated examples where you can have a bit of a nightmare with shared variables. So and just to show you how unpredictable this can be, if I put a debug.log statement in the main thread in the start method here, actually on my computer the first print statement in the new thread multiply is x times y equals 0. So this is clearly behavior that we want to avoid, because we didn't actually do any new calculations. We were just really printing out to the console, and it changed the result when we pressed play in Unity. The key to resolving these sort of problems is to use the lock statement. And the lock statement ensures that only one thread can access blocks of code at one time. And the lock statement uses a object as the key. So when it's like when one part of your code reaches a lock statement, it locks the door on various other blocks of code which refer to that, which lock around that same object. And if this is confusing, I'll show you what I mean in a moment. But although you can use different objects as a key, you can use Boolean statements, you can use a class even, it's not really recommended to use classes, and it's also highly recommended to use read-only variables. However, although lock can make your code thread safe, it doesn't guarantee thread safety. So if you're using it haphazardly or without really knowing what you're doing or what's going on with the threads, then lock can still get you into some problems, which is what this piece of code highlights here. This piece of code here, although I've used lock, is still thread unsafe, because what we get is race conditions. So in this scenario, the main thread and the new thread are racing each other to see who can get to the lock statement first. So here's my object that I'm going to use as a lock. It's called multiply lock. Now I initialize my new thread here. I tell it to run multiply, but as soon as that's initialized, the main thread lock statement here, it gets in there first, and this is called a race condition. So this gets into lock, and so because we're locking around the same object in multiply and the start method, the new thread can't get into this block of code here. So y is incremented first before the debug.lock statement can get in there, and so again it's going to print out x times y is 1. And another thing to note is that this is really computer dependent. So you might run this code and you might actually find that it does print out 0 first instead of 1. I haven't really got time to go into this, but the way to salvage this code would be to use event wait handles to avoid these race conditions. So now let's have a look at what you can and can't do threading wise in Unity. The first thing to note is that the Unity API is not thread safe. So the standard methods and functions that you're used to using in whilst programming in Unity or scripting in Unity cannot be threaded. And if you try and do it, what will happen is that you'll get an error. So I wouldn't even bother trying. What we can do, however, is use .NET Framework code, and we can also do maths and use external plugins for threading. So there's still plenty of scope if you're making a game which uses some resources from outside Unity, or using quite a lot of maths for whatever portion of your game. You can actually thread that. So have a think about what you could stick outside of the main thread, and see if you can thread that. Just a little bit of advice from my own experience is that if you read about threading in, say, C# books or programming guides, when they have a main function, and you can use while loops in main functions, whereas from my experience, while loops in threading with while loops is a problem for Unity. For some reason, it doesn't seem to be able to abort or stop threads once you stop once you press stop from the play button in the Unity editor. So I don't know why that is, and I don't know the problem, but as a result of that, I don't really recommend to keep threads alive in Unity, so having dedicated work threads in a while loop, just waiting for tasks to be updated to them. Instead, I would really recommend using the thread pool. And basically the thread pool is a collection of threads that have already been being used by the computer for tasks across the operating system, but are already initialized. And what this reduces is the overhead in initializing the actual thread, and also memory. I think I read somewhere that every time that you initialize a new thread using new thread.start, that actually creates a megabyte of overhead. Uses a megabyte of memory, which can add up after a while. So I really think the thread pool is the way to go. So now that we've got a real sturdy background on what threads are, and the certain trials and tribulations of threads, let's talk about an example which I think is really good for Unity programming, and that's queues. And basically, a threaded queue is when you have a thread dedicated to running one task or more, where tasks are queued in a chronological order. So you queue tasks from the main thread onto this worker thread, and then they just get completed as soon as this thread becomes free. And the motivation, I think, for using this structure of a threaded queue is that if you use many threads, every time you do that, you're going to be taking away from potential resources that the Unity thread will use. Now, I'm not sure about this entirely, but I'm pretty sure that the Unity API threads various things itself, perhaps rendering, and it doesn't all just run them on one CPU. But every time you use your own threads, you're taking away a resource from that main thread or the Unity threads that it's using. And this might bring down your average FPS, so that's just a word of warning with that. In some cases, you may want to dedicate a thread to long-run computations, where chronology is actually important. So if you've got a job which takes longer than one frame, then you don't want to put that in your main thread, because you're going to see spikes in your profile and in performance. You'll see a couple of frame drop in performance, and you want to avoid that. You want things to be as smooth as possible. So running things on a separate thread for long-running calculations is often a good idea, and the queues are really good ways of doing that. Also, you might want the main thread to be updated as soon as possible, but you might not be too worried about it taking a couple of frames to complete a task. You just want to get it as soon as it's ready, and but you don't want that at the cost of frame rate. So that really links into the last point. So this is the key structure that I think is that summarizes a queue, and that you have your main thread, performing your game tasks, and then events will occur on the main thread that will mean we want something to be computed, or we want to take a task and we want to load it onto the worker thread. So this thread that we're initializing to perform background tasks. And what happens is that if there's a queue, this task will get put onto the end of the queue, and then it will just basically wait until the task in front of it are completed. So when it reaches the front of the queue, perhaps we need to check shared data at that stage. So maybe when the task was put onto the queue, maybe things have updated from the main thread, since then. So we check that data, we run the task, and then we update our shared data after the task is complete. And that basically summarizes the structure of a queue, and you can keep this running continuously throughout the running of your game. Now, for the example I'm going to consider here, I'm actually going to apply it to my software, which I'm making at the moment, called Action. And instead of tasks, we have one job, so there's one task that we need to run, but different models or different entities within the game want to have basically take their turn at using Action to update some parameters. So each of these numbers here represents different models which are using Action, and those models are related to each other. And in the game, those model parameters may actually be updated in the time between it joining the queue and actually being computed using Action. So it's important at this stage that we check our model data before we do the computation. And now I'm going to open up Unity and show you how I actually implemented this queue with Action. Okay, so here we are in Unity, and this is a little GUI I've mocked up to showcase using a Freddy queue in Unity, in particular using my software Action. Now, if you just look up here, there's a little box showing the number of items in the queue, and also if the if Action, my software, is doing a calculation at that time. And I've put a command in called thread.sleep, which will basically put the thread to sleep for a little bit longer to simulate doing much harder work than my software actually has to do. So just to show you it being used, if I click on each of these skills, what will happen is that this skill gets a message which said, okay, we've got some new information and we need to update this level here. So actually, by clicking this, I increase the experience, this value here, by 0.5, and then that's used to recalculate this number here. So because there's nothing in front of, there's nothing in the queue at the moment, when I click this, it will be put on the queue and immediately dequeued and then calculated with. So this number, if there was more of a queue, this number would go up by 0.5, but it's actually not going to go up at all. Sorry, you won't see it going up. It is actually going up, but you're not going to see it. So I click, then the thread is in use, that returns false, and this number is updated. So I'll do that again, and the number's updated. So let's put a couple of items on the queue. So that's one item because I clicked that one and that one. So that one was done first, and then this one was added to a queue behind it. When the thread became free, this model was then able to use Action and update their level. One thing to note about the way I've got this set up, one model can only be in the queue once. So if I click and it's already in the queue, basically this stored experience just gets updated, and that's what I mean by in the slideshow, that before Action is used, it checks for the shared data to see the latest value of stored experience. So if I click this a lot, because it's computing, let me just pause that. Oh, I missed it. When I click once, it's already calculating. When I click again, it has to wait for that previous calculation, which I can't update. It's already mid-calculation. It has to wait for that to complete. But you can see it's actually in the queue, and it's just updating that shared value. And then when the queue becomes free, again, it can do the computation. So I hope that explains the setup. Now we're queuing 3 different items, and then they're all going to get updated as soon as the queue becomes free, as I showed in my slideshow. So let's have a look at the script which is responsible for this, and you'll see how I'm using locks and the queue structure in C# or in the .NET framework to actually achieve this. Okay, so here we are in MonoDevelop, and this is the script which is responsible for all the interesting stuff in that scene we just saw. First thing to note is that we're using the system.freddy namespace, and next thing that's really of note in the script in the class variables, is that we're actually using 3 different types of objects for locking here. So first of all, we have a locker which is used to check if the thread is free, and then each of the models has its own locker, so that the main thread, the update thread I'll call it, and the worker thread, i.e. the action thread, don't access a model at the same time. and then we have a locker around the queue as well. And as you saw before, there are only 4 models in this instance, although it can be generalized quite easily. That's why all of these arrays here are length 4 here, so the experience and that L on there. So that's why we have 4 lockers here, 4 objects to lock around the models. Probably the easiest place to start is by showing you what happens when you click a button. Excuse me, and that's on a when you click it, it calls a static method here called action. And action takes in the model that we're dealing with, i.e. which corresponds to which button, and then this parameter dx. And you'll notice here that we're actually using a nested lock to protect shared variables. So in this case, we lock around the model that we're dealing with, and then we lock on the queue as well, because the update thread and the work thread might want to access this queue and that model at the same time. So for example, if we call action and then the main thread manages to get in here, it might be that the worker thread, i.e. the action thread, completes dealing with that a particular model, i.e. the same model that the action call is dealing with, and then it will want to update the queue, and it will want to update the model as well. But we don't want to allow it to do that because we're updating it here. So that's why we have these lock statements. So in the action call, what we do is we check to see if that model's already in the queue. If it's not, we add it to the queue with the model queue.enqueue there. Sorry, I should have explained that the queue that we're dealing with here is a queue of integers, and that integer corresponds to what model is in the queue at the time. There's 2 important methods that we use on the queue, and that's queue.enqueue to add something to the queue, and queue.dequeue to take the first item, or the item that's at the front of the queue, off the queue. And so yeah, we if the model's not in the queue, we add it to the queue. If it's not, we do nothing basically. And either way, because we've clicked, that means that we need to update this dx parameter. So that's all we do here. And we notice that we've locked around that model, so it's safe to change the dx for that particular model at this time. The next place to look is in the update. And so what we do is we lock again. We lock around the queue, and we lock around this thread is free object here, because the main thread and the worker thread might be updating these values at the same time. So in the main update here, we check if the thread is free, and then we check if there's anything on the queue. And if the thread is free and the queue there's stuff on the queue, then we dequeue then basically we want to dequeue the first item in the queue and process it using our software. And this is how you call a function using the thread pool on call a method on the thread pool using a new thread. So you do threadpool.queue user work item, and then you call the method that you want to use. And so the method ace that we're calling here basically does all of the computation. When we call ace, we first of all change this boolean to say that the thread is no longer free, so we're doing a computation at the moment. Then we dequeue off the model, locking around the queue locker here again, and then the thread is free locker just before. And then in the PowerPoint I said that before we do any computation, we get the latest values of everything, so that's what we're doing here. We're for the specific model that we're dealing with, so the one that we've dequeued here, we lock around it to get all of the information that we need. And then here we actually use our computational engine, and that is a method in a different script. Here you can see that I've used thread.sleep to simulate doing some longer work for the purpose of this tutorial. But once all that work is done on this worker thread, we just need to update all the shared data again, and that's what we're doing here, and here again. And then finally we lock around the thread is free locker here, and we tell the main thread, or we allow the main thread to know that the thread is actually free again here. And that's basically all that makes up the queue. The only thing that else in this script are a couple of methods here when we want to read variables in this script from another script. So we're dealing mainly with static variables up here, so it makes it easy to there's only going to be one instance of this script in the whole scene, so we use static variables. And although we could use properties to do the same thing, I just use method calls. And when we're reading shared data, it's important that we don't just find that data and read from it, because it might be updated when we're reading at the same time, and we want to avoid that situation. So we actually lock around any data that we're trying to access, and we do that for these methods here. And that's basically all there is to the queue. I hope this makes sense. If you have any questions or would like to ask further questions about queues and threading, then please send them my way. But look forward to seeing you guys soon, and like and subscribe, and thanks very much.